Hello, I found myself with a couple of hours to kill the other night, so I thought I'd set myself a little programming challenge. What can we do regarding graphics at the console? People have been doing graphics in terminals and consoles for years, and ASCII art is an established art form now. But I thought it would be a fun series of tutorials to put together a nice complicated graphics engine. Anyway, 200 lines of code, this is what we got. So it's a little first-person shooter engine, and it's very primitive because it's rendering everything using ASCII characters. But you can see we can navigate around. I can turn the character. We can walk down this corridor. I'll just rotate us there, face the other way, and we can walk up and down the map. You can see a little map in the corner. The P indicates where I'm currently stood in the maze. We can have a quick look outside here. Let's have a look. There we go. Go back in, and we've got some blocks. So you can see it doesn't look that great, but it's a bit of fun. Let's have a look how it's done. I'm going to start by creating a new console project. And we'll call it Con FPS, first person shooter. Although there's not going to be any shooting, we're just going to walk around the maze. And I just want to do everything empty project. Don't do anything for me. And we'll start with the basic int main. Now, I'm sure if you're watching this video you know how to output to a console. But this does have a problem because it's very slow and it scrolls. So if I just tell it to do this many times, int I equals 0, I is less than a big number, I plus plus, and we run this, we can actually see it. It's drawing to the console here, and it's scrolling very slowly down the screen. In fact, if we make that a bit more clear, we can put a number on here just to show how slow it scrolls. I. And this is because outputting to the console isn't very quick. So we can't use our traditional cout method for doing this. We're going to have to grab the console buffer and write to it directly. And in this respect, we're not doing anything very different to writing to the screen, except instead of pixels, we're going to be using characters. Now on Windows, to get hold of the console, I actually do need to call some Windows functions. And I'll need to set up the console to a known set of dimensions. So I'm going to call these nscreen width, and we'll have 120 columns, and we'll have nscreen height. I'm going to have 40 rows. So this bit of code here creates a screen of type wchar, so we're going to try and do everything with Unicode. And we can see here we've got the dimensions of our array, so we're creating just a regular two-dimensional array using our width and our height variables. And we get a handle to the console with create console screen buffer. And you can see there's nothing special going on here, it's just a regular text mode buffer. And we tell this buffer that it is going to be our console, the target of our console. And when we want to write to the screen, we use this bit of code here. I'm cutting and pasting today because I don't want this video to go on for half an hour. So this is our screen array, and we're basically just setting the very last character of this array to the escape character, so it knows when to stop outputting the string. And we use the function write console output character. We give it our handle, we give it the buffer, we tell it how many bytes, and this is an interesting function because it allows us to specify the coordinate of where the text is to be written. In this case, we always want to write to the top left-hand corner, and that stops the console from scrolling down. And typical Windows, we have a variable here that isn't really useful, but we've got to have it anyway. Now with any game engine, you need a game loop. Now I got criticised for using while1 as a loop in some of my earlier videos, but I don't care. So what do we know that we're going to need so far? Well, we're going to have to store where the player is. Now for things to run smoothly, we can't use integers to store where the player is, or else he's going to clonk about the maze on a tile by tile basis. So we're going to use floating points, and we're going to store the player's X position and the player's Y position. And we also need to store the angle the player is looking at. And we'll call that player A. What other information do we need? Well, we know we're going to need a map. So let's put in some constants for our map. The map, like the screen, is just going to be a 2D array, and we're going to use the hash symbol for a wall, and we'll use the full stop to represent empty space. The game doesn't really know anything about polygons, so we're going to infer all of that from this two-dimensional map, and we'll see some tricks for that later. Let's create the map. I'm going to use a type W string because it's for Unicode. Map. And just to make the map visually easier to draw, if we use the append symbol each time, we can do things line by line. So if I want to do the boundary of my maze, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, because that's what we specified, I can take that line and we can duplicate it 16 times this way. And let's just create a big empty room to start with. It's always a good way to be debugging. I'm going to just hold down the Alt key here and select the bits I don't want, and we can fill those out with some spaces. Now I won't deny that the rendering engine that I'm using is inspired by the Wolfenstein 3D game. The Wolfenstein 3D game engine is far more capable than the one I'm doing in the console, but what I'm curious about on this excellent Wikipedia article is this little GIF down here, which looks very similar to what we've got. I've zoomed in here so we can see what's happening, and there's a 2D array of blocks and spaces, and we have an icon indicating where the player is. And as the player rotates, we see rays being cast out from the player. The result of this approach is a very compelling, yet totally artificial 3D illusion of a room. This animation is all we need to get started programming our own engine. As I'm not bothered about being able to look up and down, this is really just a two-dimensional problem. And therefore we only really need to concern ourselves with one axis, and that's the axis going across the screen. So we're going to do a computation for each column on the screen. Let's just quickly sketch up what our algorithm is going to be. So here is our player, and we're going to have effectively some blocks. And I put a second block here just to make it a bit more interesting. These represent our tiles. Now at any point the player has a limited field of view, so I'm going to sketch that in with a red line here, and we'll say the field of view is something like this. And our player is predominantly looking in this direction. Our algorithm is going to work by taking each column of the console and relating that to a ray cast within the space of the field of view. So we've got 120 columns on our screen. We're going to cast 120 rays out into the scene. And what we're interested in is how far does the ray travel before it hits a surface. So for example, we take a ray in this direction. How far does it go before we hit a wall? And we do that 120 times across this whole field of view. And what we should get is an array full of distances. This is why I have a loop going through each column on the screen. So if I add in a field of view variable, call that FOV, and to begin with we'll set that to something like pi divided by 4, which is quite a narrow field of view. So our field of view is actually this angle here, theta, field of view. The first part of this code here takes the player angle and tries to find out what's the starting angle for the field of view. So it takes the field of view and divides it by 2. And if we go back to our diagram here, we can see that this is the player angle, the red line in the middle. Here, our field of view is bisected by the player's angle. So we're looking for half the field of view this way to plus the field of view that way. And the second part of this code is chopping it up into little bits, so in this case 120 because that's the width of our screen. we're going to need a variable to track what is the distance from the player to the wall for that given angle. And to start with, we'll set that off to 0. How do we work out the distance to the wall then? Well, we take a ray and we're going to test it in little increments. So we're going to test at that step, and then we're going to test at that step, and then we're going to test at that step, and each time we keep incrementing until our increment lands in a cell that's classified as a wall. Therefore, we now know the approximate distance to the wall. It's not very efficient. I'm sure there are better ways to do this ray tracing. So we're going to need a loop, and we'll have a flag which is hit wall. Whilst we've not hit a wall, we want to keep incrementing our distance to the wall by some small step. And you'll see I'm working in the floating point domain here. Let's just add this flag in. To calculate the test point, we're going to need a unit vector which represents the direction the player is looking in. So here I'm just taking the sine and cos of the ray angle to give me a unit vector. And from this unit vector, I can create a line of a given distance. In this case, we want to extend our unit vector to the length that we're currently checking for. So this distance to wall is going to grow, and therefore our unit vector is going to grow in the right direction. And we're really only interested in the integer value of this. If we assume that all of the walls are on integer boundaries, so the edges of the walls meet on integer boundaries, everything else in between is wall, and so we only need the integer part. So if you get to a cell, say at 1.5, we really know that that's 1 in our array. We don't care about the 0.5. Now we have to be careful here because we could end up never hitting a wall, particularly if it's not been drawn in. So we should put a maximum limit on how far we check. In this case, I'm going to create a variable called fdepth. I'm going to set it to 16. It seems to make sense because our map size is 16. Now we've got our integer location, we can test in our map if we're out of bounds. So if we're beyond the boundary of the map that we've hard-coded up before, then we may as well just say, yes, you've hit a wall, we've hit the maximum distance. However, if we're within bounds of our map, we want to check the cells individually on the map. So this bit of code here is just a quick check. It's converting our 2D system into a 1D for the array, so we've got our y coordinate times the width plus x. If that contains the hash symbol, then we have hit a wall. And our f distance to wall value will retain the last value that it had, because this loop will now exit. If we just have a quick look at this animation again, really what we can see is that the further away the wall is, the larger the ceiling and the floor is for that column, and this gives the illusion of perspective. So the walls that are further away, you can see there is more ceiling and more floor, and when they're close up, there's less floor and less ceiling. So we can also emulate this projection. These two lines do this calculation. For the ceiling, we want to take the midpoint, and from that we're subtracting a proportion of the screen height relative to distance to wall. So as distance to wall gets larger, this subtraction gets smaller, and therefore we have a higher ceiling. This is why the stars don't move in the night sky, because you can assume that they're infinity away, so this all disappears and they remain in a fixed position. And the floor in our case is just a mirror of the ceiling. Now we know where our floor begins, our ceiling begins, and where our wall ends, so we can draw this into the column. So now if y is less than our end ceiling count, we know it must be, the current cell being drawn to must be as part of the ceiling. So we'll shade in our array using the same little 2D fiddle before. Screen width plus x. And we're going to just shade in our sky as being blank space. Else, if we're greater than our current ceiling level, and we're less than our floor, then we must be wall. So we'll take the same thing, earth in, and for wall I'm going to use, well, we'll use the hash symbol because that's what we're using in our map. And if I'm neither ceiling or wall, I must be floor. And for now we'll shade in our floor blank as well. Before we run this, let's set our player to actually be in the middle of our room. We don't want to be in the middle of a wall, that might just get confusing. Well, that could be a wall. Just take this opportunity of having the console window up to say, to make this to work, you're going to need to change what the properties of your Windows console is. To do this, I recommend that you use the Consolus font set to size 16, and you choose the window size to be the dimensions of the screen size that we're using, in this case 120 and 40. The other thing to do is you can set up the defaults, so each time it pops up you don't have to keep setting these values. So I've done this already here, so 120 and 40, and set the font to something that I like. So how do we know that this has worked? It just looks like 3 lines. Well, one thing to try will be to add the rotation, so we need to be able to get the character to move now. Let's add some controls. Rotations are the easy one. I'm using the getAsync key state function here, which you'll have seen from my synthesizer videos. It's a bit of a hack to use in a console, but it works quite nicely. And when the user presses, in this case, the A key, I'm going to use the WASD layout, standard in first-person shooters. We want to alter the player's angle. When we press the A key, we want to rotate counterclockwise, so we're decreasing the angle. And we're just going to put in a fixed amount to start with, so let's try 0.1. And we need the opposite for rotating the other way. But in this time, instead of decreasing, we're going to increase, and we'll change the key that we're using to a D. Let's see how that looks. Well, there's certainly something happening on the screen, but I think it's all happening far too quickly. So we can see there is a feature in there, but it still doesn't really look like a wall. Why did it look so scrambled? Well, we're turning at 0.1 radians per frame update, and the console frame rate is actually going to be very quick. One way to solve this would just be to use very small values, but that's not very tidy, and something strange is going to happen. Because our computer is sharing resources with other programs, we don't really know what speed it's going to run at, so we need to time how fast one frame is and use that time to augment the variables for movement. And this will give us then a consistent moving experience regardless of what the computer is doing. And to do this, we're going to use our old friend and very wordy chrono library. We're going to be measuring a duration, so I need 2 time points. And for each iteration of our game loop, I want to grab the current system time, calculate the duration between the current system time and the previous system time. That's what I'm doing here, updating the old time point. And I want to get the elapsed time as a floating point, because all of the rest of our game engine is in floating point. And we can take our standard movement speed, and if we multiply that by the elapsed time for both of them, this should give us a bit more consistency. Let's try that. So I'm rotating, and we can see it's a much more smooth, controlled movement this time. Still doesn't look like wall. Let's consult the animation again. What's going on here? Well, the walls that are further away are shaded darker than those that are close. This is again a little illusion. We'll need to do the same thing. Right now we're just shading anything that's a wall with this hash symbol. That's not going to be any good for us. I'm going to use a variable here called nshade, and I'm setting it to space rather oddly because I don't know what the Unicode number is for empty space. And don't forget, we're working with the console. So rather than shading with the hash symbol, we're going to need to change it depending on how far our ray is from the wall. So we're going to use this fDistance to wall variable to work out a suitable shading character. If we look at an ASCII table, we can see there are actually some characters here that have shading already. But we can't use these directly with Unicode, so we're going to need the extended Unicode equivalents. And I know some of you will be groaning, oh, it won't work on all computers and it won't work with every type of font, but you know, we're just having some fun. So we can see here the Unicode hex numbers for the different characters of the extended ASCII set. Just realised you wouldn't be able to see that on the video, so I've zoomed in on it here. So we can see there's a light shade, a medium shade, and a dark shade. And there's also, I believe, which way have I got to go? There's also a fully shaded character. And of course we've got space for a non-shaded character. So this code here takes the distance of the wall, and if it's very close we're using the nice and bright fully shaded character, and as we get further and further away we're going less and less shaded, and eventually we just have space if it's so far away we can't see the wall. Let's give this a go. Well, we can see there's definitely a change in character, but it's still not very interesting. I think we need to be able to now move forwards and backwards so we can get right up close to the wall and see if the shading is working. I've added this code for when the character is walking forwards with the W key. It effectively takes the unit vector that we calculated for the ray before, multiplies it to give it a magnitude, only by the elapsed time, so we're only walking forward consistently. So it's just updating where the player position is. And we can do exactly the same, but instead of an addition we add a subtraction. And we'll apply that to the S key. No collision detection yet. So I'm rotating the character and I'm walking forwards, and as we can see as we approach forwards the walls get brighter. Though we're rotating very slowly here, I'm going to speed this up. That feels a bit more fluid. So even though it doesn't look like it just yet, I can infer that this must be the corner of the room because it's the furthest away. And this bright section here must be the middle wall. And that must be a far corner of the room. And that's an even further corner of the room. So we're starting to get some 3D perspective, and this is quite nice because we're stood near a wall and we can see the wall changes in gradient as it gets further away. So at this point we might want to add a few extra features to our map so we can see what's going on. So I'm going to add a line down here, and I'm going to put in a couple of blocks there. So there's definitely a block right in front of me here, and we can see it's got some perspective. And we can see around the edge of this block there's a wall in the background, so it's starting to get a bit of a Wolfenstein feel. And we'll walk to this corner of the room and look around. We see the block is now shaded out. Again, consulting the little animation, we can see that the floor is also shaded. I think this helps your brain work out what the perspective is. It tells it, well, that's going further away. So we need to do the same. Let's look at where our floor is being shaded. And we can see here it's actually just being shaded with a space at the moment. We can make this a bit more sophisticated. And we'll use very similar to code to what we had for shading the walls. In fact, we'll use the same variable, but we're going to give it a different value. And so I'm shading constantly here. I'm not bothered about what the distance to the wall is because it doesn't change when you're shading the floor. The floor is always going to be the same distance away. So I'm taking a proportion of how far the floor can be seen, and as we get further and further away I'm shading it differently. But rather than using the same shading blocks as the walls, because I think that would just get confusing, I've decided to use these symbols. And I think this one is almost full, this one's a little less full, this one seems a little less vibrant, and so forth. Let's give that a go. Okay, so our floor is now shaded. I think it does help aid with the illusion. Rotate the character a bit more. There's our block that we put in the middle. Now see, that stands out a lot more now. This is our little tunnel that we put in at the map, and it's nice there. We can see the wall sort of gradually comes towards the player. Nice. As the graphical fidelity is quite low, there's a good chance as a player we're going to get horribly lost and not work out where we are. So I think we need to add some collision detection. Now the player rotating can't walk into a wall, so we only need to add collision detection when we're walking forwards and backwards. Adding collision detection is quite simple. When we project the player forwards, we want to test have we hit a wall. So the easiest way to do this is to convert the player's current coordinates into integer space and test it on our map up here, because a 1.0 floating point where our player is the same as being in cell 1. So when he hits the wall, if we check that the cell contains a hash symbol, we simply just undo what we've just done. Therefore the player ends up in the same place. So whereas before walking forward, progress the vector, we've hit a cell, we just undo it, we go back. And we can do exactly the same for when we're walking backwards, but instead of correcting backwards this time, we correct forwards. So if I just plough forwards now, I've hit a wall, I can't go through it. I can rotate out, I've hit another wall, can't go through it. But of course it's just a big blank screen, and that's why I think it's important that we have some collision detection. If we add strafing, then all we would need to do is, instead of our unit vector, we want to find the inverse of that. We'd want to find the tangent. So we just flip the x's and y's around, and we can move the character side to side. I'll leave that as an exercise up for you guys. But now I can't go into the cell, so I can't get lost. I also can't go out of bounds. So we're getting there. However, it's still... something's not quite right. It seems that it's still difficult to work out where the walls are. So I think we need to start adding boundaries. This is going to be a bit complicated. When we're doing our ray casting, we detect if we've hit a wall or not. We're also now going to need to detect if we've hit a boundary. So I'm going to add another flag. And what I mean by boundary is it the edge of the cell? Now we don't have any polygon information, we just have a map with basically a 0 or 1 in it. Am I a wall or not? And we assume that all of the cells are the same size. So here I have a scenario where the player is looking at a wall. And we've got our field of view, as before. And what I want is basically to delineate the walls by highlighting that that's a boundary, and that's a boundary, and that's a boundary. This will give us some texture to the walls and will help add to the 3D illusion. If we go back to our little animation, we can actually see that the shading here is perhaps based on the angle of the wall to the player. And I think having the blocks give you an indication of where in the room you can go. Now we're doing everything on a per ray basis, so we have to do this calculation on an individual ray, and our rays don't have knowledge of what's happened to their neighbours. So this becomes an exercise on how do we detect whether our ray has hit the corners of a block. Well, I propose that we do it like this. As the ray is being cast out from the player, as it's being searched for, we know if we've got a hit. That's how we know our distance to the wall. From this hit we can identify the coordinate of the cell, because we convert our floating points into integer space. Once we know the cell, if we trace a line from the precise corner back to the player for all of the corners, so there'll be 4 rays drawn from each corner of the cell, we observe that the ray that's being cast out is actually a very tight angle. It's very, very acute here. So let's make an assumption that if the ray from a perfect corner of the cell is very close to the ray angle being cast for the player, that perhaps we're looking at a corner. And this is where things now get a little bit tricky, because what we can see here quite clearly is if we cast from this corner back to the player, and we cast from this corner back to the player, for those 2 cells, we calculate that this is also a very tight angle, so this corner gets seen, which is clearly impossible because it's behind the front of the cell. So we need to calculate what are the 2 closest points. So just to reiterate, we're going to cast a ray from each perfect corner of the cell back to the player. We're going to look at the angle between the ray that's been cast out and that perfect ray back. And we want the 2 closest i.e. the two smallest angles, to represent the boundary of our cell, and these are the ones we're going to draw differently.
Told you this was complicated.
We know that we've hit the wall, so we need to do a test. And we're going to create a vector that's going to accumulate the four corners. And in this vector we're going to store two things. As a pair, we're going to store the distance to the perfect corner, and we're also going to store what is going to be the dot product, so basically the angle between the two vectors, because we need to sort this vector later on to tell us which are the two closest. So we're going to sort it based on distance. We've got four corners to try, so I'm going to have two tight loops, one inside the other, just to give us our offsets. And the easiest way to do this is just to create a vector from the perfect corner. So remember, this is an integer, so our 1 plus in our loop, so we're getting the perfect integer corners offset from our player position. This will give us just a vector from the player to the perfect corner. Then I want to calculate the magnitude of that vector, so I know how far away the corner is from the player. And at the same time, I may as well calculate the dot product. So this is going to be a representation of the angle between the ray being cast at the moment, which if you remember our unit vector from before, Fix and Fiy. And it's the dot product between our unit vector and basically the unit vector of our perfect corner. And I want to assemble that into a pair and push it into our vector. Now, thanks to modern C, the easiest way to sort a vector is to use a big nasty lambda function. And if you look at my 8 bits of C++ code you should know video, there's quite a detailed explanation of lambda functions. But I'll talk you through this one. So we take our vector and we're calling the algorithm utility sort, which takes a starting point, i.e. the whole vector in this case, from beginning to end. And here we've got our little lambda function. And the lambda function takes a type of pair, because we want to compare our pairs based on distance. So we're going to sort this from closest point to the furthest point away. And our lambda function takes in the two pairs as arguments and does a simple Boolean test, is one smaller than the other. And it's based on the first element of our pair, which is the distance in this case, d up here. Now this angle that we're going to be testing is a little bit subjective, so I'm going to make it a variable that we can play with. 0.05 radians. And the calculation that we want to do is we want to take the inverse cosine of the second part of our pair for our vector. Remember, our vectors are sorted now. I know, this is getting worse and worse, isn't it? Our vectors are now sorted, so the second element of the vector was the dot product we calculated. And if you take the inverse cosine of the dot product, you get the angle between the two rays. And what we're looking for is now very small angles. And if our angle is less than what we've specified here, then we can assume the rays hit the boundary of the cell. Now we only need to really test for the first 2 or 3, because you'll never see all 4 in a normal Cartesian space projected normally. So let's have a look at what this looks like. Oops, silly me, I've gone too far ahead. We've not done anything if it is a boundary, so let's shade in the wall differently if it's a boundary. I'm going to do this very simply. If we have hit a boundary for this column, I'm going to black it out, but I think just for now I'm going to make it stand out more, so I'm going to set it with an I, so we can see where does it think the boundaries are. And if we run this, wow, lots of I's all over the place, so it thinks there's boundaries everywhere. It's kind of working, so we can see that there's an individual cell here, but there's far too many columns being attributed to being a boundary, so it just looks a bit of a mess. Let's adjust our bounds parameter here. Let's get this nice and narrow. So we've not given it much scope for error. Really, the ray has to hit the perfect corner for it to be seen. Well, that looks a bit better. So it's on average attributing 3 boundary columns to each cell. Let's go and try and find our features in the room. There we are. So we can see our 2 cell feature here. It's nice. It's found the corner quite sharply there. And if we look at it from a slightly odd perspective, it's found the corner, but it's not found this corner here. Let's see if we can do something about that. And that's because we're really only displaying the first 2 that comes back. And you could technically see 3 edges to a cube in 3D space. Let's throw that in. We'll look at the same feature, and now we can see it's highlighting that corner, and that corner of this one cell in the middle. Let's change it from the eye, that's a bit distracting. We'll put that back as a space. and now it looks like it's part of the texture of the room. Very nice. Oh, even better, it kind of gives us this bonus effect that it looks like shadow. And that's because we're almost parallel with the plane of this row here. And so a lot of those boundary calculations will come back as being a hit. It's hit the boundary. So if we make the angle a little bit more obtuse, you can see they don't bunch up quite as much. And that's a really nice little 3D touch, I think. And we can also get a feeling for the amount of space. So we can see that this corridor is 2 cells wide, but the wall is only 1 cell wide. There's an interesting thing. Because we've got it showing the 3 closest points, this what looks like an erroneous black line is actually the other side of the cube. So that's something to think about. I'd perhaps just set it back to drawing the first 2. I'll leave that up to you.
It's still quite easy to get lost in our maze, so I think we'll add a map.
We'll not just add a map, we'll also add some stats telling us where our player is, what the angle he's currently facing, and we'll throw the frame rate in. It's a first-person shooter. Can it run Crysis? Yes, it can. And to get the frame rate, of course, we're measuring the elapsed time per frame, but if we remember that f equals 1 over t, so frequency equals 1 over the elapsed time, that's the equivalent frame rate. And drawing a map is nice and simple. We're just going to go through the coordinates of our map and directly put them into the screen buffer. I've offset it here by 1 because I don't want to overwrite the stats that we've just put out at the top. Because I've not specified a coordinate here, our stats are just displayed at 0, 0. I just want to add one final touch. I'm going to add a marker to show where the player is. So I'm going to draw the letter P somewhere in our map based on the integer versions of our player coordinates just drawn in on top. Let's have a look. So as I'm approaching the wall, I can turn around, I can see my little player here. If I put him near the edge of this column, we see he lines up nicely, that's good. And we can navigate the maze. And it's running at a nice 300 frames per second. And that, don't forget, I'm also running my screen capture software, and we're running in debug mode. Let's crank this out in release and see what happens. So wow, release mode has gone up to almost 7,000 frames per second. And we'll see that it fluctuates as the rays have further to go before they hit anything. More calculations have to happen per column. This is why we added the elapsed time, because even though the frame rate is varying, the perceived movement of the player doesn't change. Very nice. All I need to do now is add some bad guys and some bullets, but I'm not going to do that in this video. I've gone on long enough.
So there you have it, a first-person shooter at the command line. I know it's daft and a bit silly, and it looks a bit crude. But it got me thinking. When Wolfenstein came out, it revolutionised how people thought about doing game engines. But I believe that it's quite clearly possible to do this approach on old computers. It must be that nobody had thought about doing it. At least not to my knowledge. Most dungeon crawlers were very static and quite boring affairs where everything was at 90 degrees and you took one tile at a time as you crawled through the dungeon. I'd be very interested to see if anybody out there could port this over to an old machine and see how well it runs. Perhaps we would have far more advanced first-person shooters today had it had the 5-year head start using a very similar technology. Anyway, if you've liked this video, please give me a thumbs up, subscribe, spread the word, and the code is all available on GitHub from the link below. Take it, do what you want with it, hack it, have fun.